Hi again, everybody. Welcome back. Welcome to week, I guess, 11 of the semester. Finishing up lectures this week. Of course, not finishing up labs, and the project is the thing that should be on your mind by now. The thing that's on my mind for today is, I guess, other big data tools, sort of broadly. So a bunch of like a survey in this last slide deck. But before we start there, I want to talk about a few specific like tools that can let you do stuff in parallel with in Python. So of course, like Python's not the only language to do big data with, but it's certainly a common one. It's nice to write. There's a lot of data management tools. There's a lot of libraries for like common data manipulation things just in general available. So why not, right? We've done a fairly deep dive on Spark, but certainly it's not the only tool for, well, certainly not the only tool for data manipulation. I talked about pandas and small data tools last week, but to go a little bigger, to do things in parallel, not the only one either. So maybe I'll mention Celery, which is a task queue for Python. And I'll do a demo of this later in the other big data section. But the idea here is that you have tasks, which are basically functions that have a little bit of extra decoration on them. So I have functions that can do some work, and I can call those asynchronously. So instead of just calling the function, give arguments, get a return value like I normally do, call a task, it will run somewhere. A message is sent over that says, we need this done with these arguments. It happens in one of the Celery workers, and the return value comes back if applicable. Like you don't have to return a value. You can just say, okay, go do this. It needs to be done sometime. Or you can wait for it to be done and get a return value from the task as well. I'll also mention a little bit of RabbitMQ later, but RabbitMQ is a message queue tool, and it's good. It's very good at passing messages, I guess analogous to Kafka that we've seen. These will scale, and I guess the big data sort of fact here is that you can have many workers. So you can put 1,000 tasks in the queue and have 100 workers grinding away at them, and they'll get done, sort of as soon as possible. And RabbitMQ makes sure those messages get back and forth. That scaling makes it a big data tool. And like I said, I'm going to do a demo of that later, so I'll hold off on details for now. I do have a bunch of demos today. We'll see if they work. It's always a bit of a gamble, no matter how much you prepare a demo. So Dask is a tool that is relatively new, and it kind of fills in a gap almost in between pandas and Spark. So there's things that I like about pandas, or at least I can say I like about pandas for the sake of argument. I like the method call. Like I like the way I do work in pandas. The methods are more rich. There's more you can do. I'm pretty used to Spark. I'm not sure this is true for me, but in general, more people have more experience with pandas, and just being able to do the pandas method call is desirable if you already know that. And this is also, like Dask is also sort of looking at NumPy and scikit-learn and saying, well, we like those too. We want to be able to call the same functions, same methods, same arguments. But lazy evaluation turns out to be really nice in Spark. I know, as you're working with Spark, you sometimes fight with it, and it can be hard to figure out, I did something wrong, but where? But once you get things working, that lazy evaluation lets the Spark optimizer do its job. It lets the compute be scheduled across a compute cluster, and we want that to be distributed. We want to be able to do pieces of work in different threads, processes, computers, whatever. So I'm going to recreate this most viewed Wikipedia, just because I sort of, I looked around our assignments for things that would kind of be good. So I got this. Oh, whoops. There we go. So, well, you know what? It's on the slides. I won't. I have the file, but the details are here. So, if you've worked with pandas at all, the sort of this style, right? So the thing you would often do in pandas is say import pandas as PD. So you have this thing that you can use. So the Dask data frame library is sort of analogous to that. I'm going to create something called a client. And that's basically, or the default here is just do work on the computer, on this computer. But it could you could be sending the work somewhere else if we start it up a little differently. So when it comes time to read the data, I guess maybe let's look at the data set. So it's a page count with time. I guess it's compressed. So it's gzip compressed, but I have data like this, right? So it's space separated. But it turns out if you say it's a CSV and say your separator is a space, that's good enough. But this is what I've got in the files. So I've said there's no header rows. I've said what the column names are, pass that in. But mostly what's happening here is if I put df.readcsv, pd.readcsv, you would recognize it as pandas. It would be exactly the same as pandas, except in Dask, I'm allowed to say star, so I'm allowed to read all the files in a directory, which is what that code is doing. In Spark, we didn't have to say that. Implicitly, we were reading a whole directory. I might not have sort of pre-partitioned inputs, and I can say stuff about partitioning as you read to Dask, which I can't say in Spark, and I can't say in Pandas because there's no concept of partitioning. Otherwise, these things are straight out of Pandas. And I have a data frame. A Dask data frame, not a Pandas data frame, not a Spark data frame, a third implementation of the data frame concept. And then I can work with it. And it turns out all of this code is exactly Pandas code. Like if I sort of replace this with a Pandas data frame, I can copy and paste this code. It will work exactly unchanged in every way on a Pandas data frame. So the sort of promise here is that if I'm going the other direction, if I have this and I'm doing the work in Pandas and I realize my scale isn't, Pandas isn't quite up to the task. I need multiprocessing and I need to scale out across a couple of computers or something. Maybe I can just change the way I start. Create a Dask data frame instead of a Pandas data frame. Maybe I can reuse the rest of my code. And in this case, it would be true. So again, this is what we did, right? So keep only the things that are in English, throw away the things that are titled ways we're not interested in, find the maximum views for each hour and join back. So there's a join method in Pandas and a merge method, and I can never keep straight how they're different. This time I need merge, but it's equivalent to this is equivalent to the Spark join that we would have done. Join that back so the max is found and we have the title all together. And then this is also exactly the same as Pandas, except I'm creating a directory instead of a single file, like a directory of many files instead of a single file. And I guess the other difference between Pandas and Dask is when I wrote all of these lines of code and when these lines of code executed, no computation got done. Effectively, I just built an execution plan like I would have in Spark with lazy evaluation. And this is the moment when the execution plan actually gets evaluated, which I feel like is kind of disorienting. Like if I was a Pandas only programmer, I had never seen Spark, I'd never worked with lazy evaluation, taking the exact same code I'd written before, where this would be a data frame with some stuff in memory, and now it's a data frame that is effectively just an execution plan that will happen later, or actually not happen in itself. It will be incorporated into this execution plan. That would be really weird. Maybe I'm glad I started with Spark. The mental shift to have the same code behave so differently would be funny. But once that happens, we can go for it. I think that's the command I want. I've already installed the thing. So now it does the thing and it works, I promise. It created a bunch of output. Again, I still have some sort of weird partitioning, but oh, right, it's gzip compressed, but not in the file name, strangely. Anyway, so yeah, I have what would have been the right answer. Like that's what I sort of expected, broken up into a bunch of files. There was some concurrency happening there, I promise. It happened pretty quick. It's hard to see it. But we can actually see it if we hit it hard enough. So I'm just going to put this at the end. So the input here is pause, like wait for me to type a line. Like basically wait for the user to press enter. I want to keep this program alive long enough to explore this web front end. And I've done this. So the execution plan that we look at in Spark I don't know if there's any good way to, in Dask, we get this. So we're seeing every partition, which is a little odd. So I had 4 input files when I created this image. So this input file gets stuff done to it. And you can kind of see, like, it's not maybe as verbose as a Spark explain, like execution plan, but this is take the pages where the language is English and the title has some properties. And so take the thing and get, this is probably equal to English and where is it? Starts with and is not equal to something. So that's that sort of path that we followed up there. And then we do the group by and max. So there's a group by on each partition as well. We put all the partitions together and take the global maximum. So I guess, this implies, again, something like a combiner, I guess, if I'm reading this graph the way I would like to. And then we join those back together to get our final results. So I can see that, and that did just get created there when I ran it as well. I have more than 4 input files, so the plot is somewhat worse. Again, it's a lot to look at to take every single input file and draw it, but at least now I can see, like, is there anything like a shuffle operation, right? So if I sort of follow this file, there's no lines between these sort of towers of calculation. They can be done completely independently until those 2 lines must join. I mean, somewhere in here they join when I do this group by, right? Right. Sorry, these paths converge here. So I do this group by, and then so I can look in this graph and see exactly what sort of operations on each partition can be done independently. The other thing that I can sort of infer from this graph is Dask is analyzing at this different level. I didn't have to cache in Dask. It can see the entire thing that's happening. I don't have to tell it to cache. It can see the entire calculation and sort of figure out, there's 2 arrows out of this node, so I'm going to need it twice. Okay, so the other thing that's happening here is the web front end. And I think I have 3. Maybe I can get enough work happening that I can see it. And I get this cool, like, animated, I don't know if I can make the font size work, but this is, as the job is running, I'm seeing like what each thing is as it happens, like where the time is going, what each executor is doing, or whatever Dask calls them. So, most of the time is reading the input files, and I guess I'm done there as I say this. There's some time in the group by operation and whatever else is happening here. The red looks like moving data around. But yeah, I can see all of these things happening. I guess this is probably the graph that is that dot visualize if it eventually loads. Let's not push it. Um, it's kind of a nice, it's a cool, it's somewhat sort of a more modern web front end than Spark ever gave us, which, and the Spark one is not horrible. So that is kind of cool. It's a nice tool. That startup that's happening where in the code there, I just said client equals a client object, and I got the defaults, which is all of my, I think it's gone now. I got enough workers to use all of my CPU. So I have 4 workers, each one has 3 threads. So in total, that's 12. I have a 6-core, 12-thread CPU. That sounds right. But there's a bunch of other stuff you can do too. And again, like as defaults go, that's a pretty good one, right? Use all of my CPU cores on this computer. Cool, great default. You can also start up this like impromptu cluster where you can say on one computer, start the Dask scheduler, the sort of master node work. I'm going to say it's at that IP address. And then on sort of as many computers as you feel like, as long as you don't have like firewall problems in between, you can say, be a worker and contact this scheduler, please. And this is something like I actually tried this one day in the computer lab on campus. Just I was there and there were no students asking me questions. So I sat down at one computer and I started the scheduler, and I moved over to the next desk and I started a worker to talk to it, and then the next desk and the next desk. And then all you have to change in your code is say, well, contact the scheduler and let it tell you, where jobs can be assigned, or let it assign the jobs, however that should be phrased. There is some assumption there that this will work everywhere. Like I do need sort of shared file systems in between. Like if I'm going to read this data, it has to work on any computer where the worker is actually running, but you can get there. That's also very interesting. Again, a very cheap way, like very minimal sort of system administration to get a little bit of distributed computing happening. There's also, if we sort of come over to their docs here, so the single machine scheduler is the default thing, I think. Or you can run on like a supercomputer. Like Slurm is the thing that would run on like Cedar, the supercomputer that's on campus, or if you have Kubernetes infrastructure, or you can run it on a Yard cluster. Well, we have one of those. All of these things are, and again, it's not like I've tried them all, but in theory, at least, Dask can deploy itself in the same basic code on any one of these schedulers, which I guess we've seen that kind of thing in Spark as well. A different collection of schedulers, but same code in a different situation. So I managed to do this on our cluster. Like I managed to get a Dask job starting on our compute cluster. I couldn't get the Python HDFS library to talk to the HDFS, so I'm sure it's possible. The perfect combination of libraries or whatever didn't happen. So again, like Dask looks like a really promising tool to me. It also has more tricks. So I've been talking about the data frame functionality that Dask has. It turns out it will also do arrays. On their front page here. So if the sort of pandas replacement is like a data frame but partitioned, right? So I have a Dask data frame that is made up of many pandas data frames, and maybe they're actually implemented as each one is a pandas data frame, which is implied by their picture here at least. Or if I want just really, really big arrays, I want to do NumPy array work, it will chop up an array into pieces and handle different pieces on different workers. Or there's DaskML, which is a scikit-learn reimplementation on this sort of foundation. That's really cool. There's also sort of more low-level, I guess, tasks. Like instead of just saying, okay, I have a data frame thing, you can just say, I have an arbitrary Python thing that needs to be done. So I have this, so this is a function that takes one argument. This is the argument. So this is a thing that could be computed in the future, a promise in JavaScript speak. And then whatever that is, eventually I can call the .compute method and actually have the thing done. So I think there's more complete code down here, right? So I have just normal Python functions that do whatever. They take 1 or 2 arguments or something. I have a whole bunch of, these are, oh, sorry, this is just straight, where's the Dask version? There we go. This is the Dask version of that same thing. I'm going to do a whole bunch of that. I'm going to start up all of these tasks, or I'm going to sort of queue up all of these tasks. And I think here, even in the code that's shown here, nothing happened yet. Eventually, I will say .compute. And then this entire graph can execute as a unit. And, it can start doing these things in whatever way it wants to schedule them. In fact, on their front page, there is like this example of some hugely complex computation that they've done. All that Dask really has to do is do a sort of traversal of this tree in whatever order, because we're trying to get from the inputs at the bottom to the output at the top. And again, in whatever order these things are done, as long as you sort of follow the graph dependency order, we can do it. And again, in one thread or 1,000 threads kind of should work. Seems like a really cool tool. What I'm not clear on, and I'm certainly not a Dask expert, I don't see nearly the number of sort of tools that let us get all of that performance out of Spark. If I was working on data on the like terabyte level, I am not at all sure that Dask would keep up. How does the optimizer work? Can I repartition if I need to? There is some repartitioning there for sure. It feels a little young. Like if you go looking at the documentation for data frames, what you'll find is a whole lot of what feels like very incomplete documentation, because I think there's just this implicit, like, we do what Pandas does. All right, so I don't know if I want to drop. Okay, it does say, but I kept finding things. I think it was when I tried to do the read CSV. Not all of the arguments are actually even in here or in explained in the docs, because implicitly there's all the other things that you can do in a Pandas read CSV. You can give those arguments too. These are just ones that are sort of new to Dask. So everything, oh yeah, it's just like Pandas, except I tried to sort my output and I found out there is no sort method. It just does not exist in Dask. That one, I did the same thing as Pandas and it doesn't work. And again, it's just not clear from the documentation what will and won't work. You have to explore, and maybe the next version they will implement sort values and I'll be a liar. Again, like I said, it looks like a really good way. Like if I have a whole bunch of Pandas code that's doing work and I need to scale a bit more, I think this looks awesome. If I did have a lot of data, again, if I was genuinely looking at a big data set, I would probably start with Spark. It looks better and looks like it's going to scale more. Like maybe in my head, I have this like megabytes use Pandas, gigabytes Dask or Pandas, terabytes Spark. Or again, like somewhere in the middle, they're all going to overlap, but cool tool to have around. And again, I think I'm glad I had a few minutes here to talk about it. I think it's worth you knowing about, because again, I think there is the real possibility that some of you will end up in a position where there's been some sort of very impromptu data work done and it's been done in Pandas, or because that's just what they had or what the intern knew about or whatever. If you need to scale that and you don't want to rewrite the entire code base, this looks like a really cool option. Another option down this path, Ray and Modin, which I'm not going to talk as much about or do a demo. But the idea here is Ray is about, again, like distributing computation. There's tasks and actors, and again, you can say like, here's effectively a function that can run remotely. Again, arguments come in, return values come out. And then if you need some data to be held. That's a class, which wrapped up in Ray becomes an actor. And Ray takes care of getting all that done, right? Again, like you have all of these tasks that need to be completed or actors that need to be scheduled. Ray will make sure they get done, again, in a sort of distributed, possibly distributed setting. And I'll leave that tutorial there. Modin is the promise of replacing pandas, but on top of Ray. And again, their promise is, so again, usually you would say import pandas as PD. Their promise is that you can import modin.pandas as PD and it will just work. I mean, not everything will just work. And I see how you could get yourself into trouble here. Right? So what's being conveyed here is Modin data frames are partitioned, and things that are implemented in Modin are operated on the partitions concurrently, not all in the same memory on the same computer, that kind of thing. But if you call a method that is not implemented in Modin, they convert to a pandas data frame, call the pandas method, and come back. So your code will work, and it will work on your small test data. But this feature makes me, I mean, it works. Like your code will work. That's great. But I see how you could very quickly get yourself in trouble by calling a method that looks like it works just fine, but then ending up in this situation where it doesn't work because you have too much data and you're back and forth between pandas all the time. So this is something where I can't keep track, to be honest. Dask looks really cool. Modin looks really cool. Both of them are effectively like pandas, but faster, right? We like pandas. We like the pandas API. We wish it wasn't in memory and single threaded and strictly evaluated. We like lazy evaluation. We like distributed, or in some of these. So all of these things are kind of in that category, like pandas, but faster. Like Rapids is, we like pandas, but we don't want to do the computation on the CPU. We want to move our data into the GPU and do the calculations there, please. I have no idea how useful this is or how realistic. Like in their example code, it looks like I can almost treat it like a pandas data frame. I can do many of the same things, but again, with the promise that I get the speed of my GPU, but then not every operation is possible in a GPU, and it's complicated. Again, these other ones, I can't even keep track. And we can argue maybe that Spark data frames are like pandas, but faster. I certainly don't know what the right answer will be here in a couple of years. My gut tells me that pandas isn't going anywhere, that Spark isn't going anywhere, and that Dask is going to get bigger. But I don't know. Keep it in mind. Keep these in mind. Which one? Swifter is the one from Databricks people, maybe? One of these, maybe it's Koalas. Koalas is from, given that it's databricks.com. Databricks are the people that created Spark. So their pandas replacement seems like it ought to be pretty good. Like they have most of the things you can do in pandas. I don't think I've ever even started a koala's job. It's probably really cool. Feel free to explore. Okay. What I want to do in this slide deck to sort of finish things off is, again, do a bit of a survey, expand a little bit from what we've seen in this course. There's lots of big data tools out there. Like this big data ecosystems table is almost like depressing in its size. Like, I don't know, if I scroll randomly, Facebook Apollo, do I need to know what that is? Do you need to know what that is? It's a Facebook Paxos-like NoSQL database. Those are cool words. Do we all have to know Storehouse? What's that? It's a library to work with asynchronous key value stores by Twitter. Huh. TokuDB sounds cool. Great name. Love databases. So again, it's depressing to me when I look at these lists because there's no way I can or you can or any single human can know a large number of these things. And I guess I will point out they're not all strictly speaking big data tools. D3 is a cool visualization tool in JavaScript, but not specifically big data. Some of these are just data tools. Within the umbrella, like Apache Big Data umbrella, where you will find things like HDFS and Yarn and Spark, there's all these other things. Is Apache Kibble important to us? Probably not. Will it be important to us next year? I don't know. And then, of course, there's all the things that are provided by cloud computing services. And if I like this Amazon Web Services in plain English page for nothing else other than I can never remember, like, what's Elasticache? Oh, it's memcached, except in Amazon, and it's not exactly memcached, but if you know what memcached is, this totally explains it. Amazon EC2, Amazon Virtual Servers. Yes, that's what it is. Thank you, AWS in plain English. This page might be worth a look just if you find yourself like confused by Amazon jargon. Maybe, yeah, Amazon Data Pipeline. Yeah, it's Amazon's ETL tool. Elastic MapReduce, that's Amazon's Hadoop thing. Yeah. Again, totally worth a look if you are interested in such things. But I want to, I guess, talk about a few more things kind of within reason, things that I have a sense are actually kind of usable and and used by people. It's a moving target. I'm not sure I can hit every highlight perfectly, but maybe these are things that you just need to know might exist, or might be useful in a particular problem you have. So I'm going to break this into two parts. The sort of part one, we have seen these before, but there's other tools that do the same fundamental job. And then the ones where we haven't seen something from that category. Okay, things that we've seen before. For example, we've seen Yarn, where fundamentally the job of Yarn is I have a task, I have a job, an application, whatever we're calling it. I have some compute work that needs to get done. It needs some memory to do that. It needs a GPU or whatever. I need resources. I need compute resources. And fundamentally, that's what Yarn's been doing on our compute cluster. It's give me this many CPU cores. I've got to compute some stuff. Mesos came from the AMP lab in Berkeley. Spark actually started as like a demo of what Mesos could do originally. So again, like the same idea. It's run this on a bunch of computers. Somehow you can then schedule work to happen across your compute cluster. Down the same path, like in some ways, just something like Amazon EC2, which is just, I need a virtual machine, please. Maybe that's just a way to get some infrastructure where computing can happen. Or I could use Amazon Elastic MapReduce, which is virtual machines plus set up Hadoop for me, please. Then I can get compute done. In some ways, any of the things that are like, platform infrastructure, platform as a service, right? The thing where you effectively get a function call, App Engine and Amazon Lambda being in this category, where I just want this to effectively, I'm going to call a URL that implies, again, like some compute work is going to happen because I've hooked up that URL to a function I wrote, and then I'll get results back. Amazon and Google can scale those calls up a lot. If you have a lot of work to do, maybe that's a way to have them scheduled. Or the things like Kubernetes, or what, again, in plain English is Amazon Kubernetes, things that will schedule Docker containers, and sort of allocate those Docker containers to physical hardware where they can be run. Maybe those are ways to get compute done, to say, okay, I have this Kubernetes job. I have all of these things. I need 100 copies of this container started up. to do whatever, and Kubernetes can schedule it as it is possible, I guess. In some ways, I'm not so worried about this one. Like, I feel like Yarn, and maybe I should put like the Dask clustering tool on this list as well that I just mentioned. Like, Dask has a tool where it can do this for you. Probably the part that I care more about is, well, as a programmer, what do I say? Like, how can I open up a text editor and type some code that will express computation? I mean, that's a program. That's fundamentally what every program is. But I want that to be distributed across a cluster. So this is what we've been doing in MapReduce and Spark. Fundamentally, it's expressing a computation that needs to be done. And if we express it this way, it can be done on a compute cluster. Flink, which one's Beam? Okay, Dask and Koala. Again, Dask is the one we just talked about. Koalas is from the nice Databricks people. Both of these are Pandas API. I forget again. There's so many of these. Beam does actually seem to be in active development. Flink, I think, is as well the last time I looked. Flink is sort of focused on streaming data. Well, if you're focused on, so this streaming first promise, I mean, you could think of any streaming, like you could think of Spark streaming as just, okay, every job I write is a streaming job. Oh, except some streaming jobs have a definite endpoint. Like when you've looked at all the files in this directory, that's the end of the stream. Well, then it's no different than a normal Spark job. You just stop when you're done with all the files. But you think of everything as streaming. Yeah, why not? Sure. If streaming's important to you, maybe you want to always work that way. Hive and Pig, okay, wait, no, sorry. So Hive is effectively it's a little bit data warehouse feel to it. You write SQL queries or almost SQL queries, but those can read data from a bunch of different sources, almost like you can in Spark data frames, right? So in a Spark data frame, you can do basically a SQL query, but with a huge variety of different input and output sources, kind of like Hive. Pig is this funny scripting language that basically compiles to a MapReduce job. It's weird, but I guess if your other option is to write full MapReduce jobs, it's probably much nicer. And then, of course, and I should maybe put in all of these categories. In fact, I will put in most of these categories, just programming. Like, you can just write a program and call a network thing on another computer that does some work for you, and open up a TCP socket and send messages back and forth. All of that is a perfectly reasonable way to distribute computing across a bunch of computers. Maybe you don't want to. Maybe you find working with Spark or Dask or something, on top of Yarn much easier. It probably is. But if you don't have that option, okay, you can just make a network connection to a program running over there and share partial results back and forth. Why not? Data warehousing that I talked about, again, fundamentally take a bunch of data sources and collect it in one spot, or do data analysis. Well, again, either collect it in one spot so you can do data analysis, or read it from where it sits and do the data analysis. Either way. And again, we've done a lot of this with Spark, and especially with data frames. Like I mentioned, Hive is a way to express this with really data warehousing in mind. And then a bunch of specifically data warehouse tools where you can take the data from a variety of inputs and do stuff with it. I don't think I have anything specifically to say about this. Of course, the cloud providers have a thing to sell you. I bet the thing that they sell you is easier to set up than Yarn and HDFS. Is it any better once you get it set up? I don't know. When it comes to storing files in a distributed way, right? So we've always, ever since you first had a computer, you can put a file on a disk. The question here is, well, I want my data to be distributed so I can work on it with a distributed computation tool, or maybe it's just so big it's not practical to keep it on one computer. Maybe I have real files. Maybe I have something that's kind of enough like a file that I can use it for compute work. We've been using HDFS for that. Amazon has a thing for that. So do the other cloud providers. The thing that's an object store, I guess, is a generic term for this. And it's, well, again, it's not quite files. It's Amazon is storing files. You don't interact with it like it's a file. You interact with it like it's an S3 object using the Amazon S3 API. And that's fine, as long as the tool you're doing can read and write it. And then on Amazon's side, they can distribute that across a bunch of computers and load balance as they feel like it. Gluster is what's used in our supercomputer, and it's, again, bunch of machines that all sort of coordinate with each other and keep various slices of the data set. And I guess one of the other things I need if I'm going to talk about distributed anything is redundancy. So I need some idea here. If I have a bunch of computers in my Gluster cluster, what happens when one disappears? How does it take care of that? And I think that the answer for all these is they do, but how? And is it in a way I'm happy with? Ceph is another open source sort of infrastructure tool. I think a little bit more built on, like, I'm going to run all of my company's storage needs on a collection of on a collection of physical machines, and that's going to back up a whole bunch of virtual machines that do the compute work. But again, big and distributed, and it offers, you can do like just mounted remote file system, but you can also do something much more like Amazon S3 and just have objects that are stored across your many file servers, or just have file servers, right? Again, you can have those. Now redundancy is my problem if I just have like a bunch of disks on a bunch of computers, or if I have network attached storage. Again, probably that's good enough. Probably for most cases, the networks and the disks are fast enough that just normal storage arrays are going to do the job okay, but it depends. What are you doing here? It's maybe worth looking into. So certainly you've seen databases before, but again, we've sort of broken databases into two categories. And we have the NoSQL databases like Cassandra that we use this semester. And this is, I care more about distributing my data storage and my query handling than I do about ACID guarantees and relations. So, okay, Cassandra seemed pretty good. It clustered. We got secondary keys. That was cool. We didn't get joins. That was bad. HBase is the one, the sort of from the Hadoop ecosystem. It is very good at what it does. It is very well distributed, very fast, and it's like the difference between like driving a Tesla and driving a manual transmission truck. It's so like, okay, here's how manual HBase is. HBase has exactly one data type, a byte array. If you want to store data, that's fine. HBase will store any bytes you want. If those bytes happen to represent a floating point number, that's fine. Doesn't matter. HBase doesn't care. It will store bytes. And if you want them to be a floating point in your program, you have to convert those bytes back to a floating point number when you read the result back in. That's fine. It kind of removes any like data conversion or any management of your data types from the database. So it's great, right? We'll pass that off to the programmer, but it now means it's the programmer's job. Every damn time you want to touch something, you have to convert bytes into the data you think that those bytes represent. And then if you want to store it, convert the data into bytes and send that to HBase. MongoDB is a common choice. Don't use it. Like, honestly, MongoDB, everything I've seen says it was not designed to be reliable in the way that I expect a data store to be reliable. Or maybe think of MongoDB as a caching layer. Perfectly good caching layer. It's clustered, it's fast. Sometimes it doesn't store data properly, or it fails in an inelegant way and takes forever to recover itself. If what you're keeping is a secondary copy of your data, I think that's maybe acceptable. I would caution very strongly against using Mongo for any data set that you actually need to be working tomorrow in a critical way. And again, the various cloud providers are happy to sell you a big distributed database. But sometimes I like SQL and I like relational databases. Now, of course, there's the normal ones, right? The ones that work on one computer. They will still hold a lot of data. They are still quite good at what they do. There's this relatively new category of NewSQL databases, which is basically we had SQL databases. The NoSQL crowd said, oh, no, we don't need all that complexity. We need it to go fast instead. And then the relational database crowd said, oh, did you want it to go fast instead? Or did you want it to be distributed? Oh, we can do that if you want. And Amazon Aurora, I guess, being an example of that. It's not at all clear to me, like if you have data that's a little bit too big to be comfortably dealt with in Postgres, I think probably these NoSQL databases are an excellent choice, right? I thought there was a list here. Maybe this page has been edited since I last looked at it. Anyway, it's not at all clear to me that the NewSQL databases will scale as well as Cassandra, but they will scale more than the sort of standard issue old school SQL databases. And again, depending on what you're working with in whatever future you're imagining, maybe it is worth knowing about these. Most of them aren't terribly cheap, but they will do a job. Another problem is that this sort of conversion between, like, I have data, right? I have strings and floating points and whatever I have in my data frame or whatever other data structure I'm imagining. How do I turn that into bits so I can save it on disk or ship it over to the other computer, or even just to represent in memory? So these ones, Parquet, HDF5, and then of course we saw CSV and JSON a lot. These are fundamentally ways designed for disk. These are, I have data, and again, specifically I'm thinking about data frame kind of data here. How do I write that to a disk? Again, in a way that I can read it back in quickly, or so that if I ship it over to my friend in the other department, they can read it or whatever. I think for us, Parquet probably should be the default format. It's supported by lots of stuff. HDF5 feels a little old-fashioned to me. I feel like when I see it, it tends to be in older tools and Parquet in newer tools, but that is a very subjective thing based on obviously limited understanding of the universe. I mentioned Apache Arrow, which is really designed for in-memory representations of data frame-like things. Spark does it, Pandas does it. A bunch of the other sort of do computation on data frame like data tools will support it. I thought there was there we go. That's the thing I was thinking of. Yeah, so Pandas, Rail, Impala, and then you can sort of read from Parquet, Cassandra, HBase into an arrow representation in memory, and then any of the tools can read that memory, or they can exchange the same representation. And I also talked briefly, 2 weeks ago about Delta Lake, as it's effectively a layer on top of Parquet, where the ACID guarantees and the sort of transactional kind of thing that you would do in a relational database can be done on Parquet files. So again, it's destined for disk, but with some nice sort of behavior added on top, I guess. So we've seen Spark streaming again. So this is data arrives in a stream, right? So I have data that is just coming. It's coming from the sensor or from the Twitter API or from wherever it's coming from the message queue. I've just got to process it as it arrives. I can't let it back up, or I can't let it back up too much at least. So again, Spark structured streaming being the one that we worked with. There's a few of these other Apache tools. Well, sorry, a few Apache tools in the Amazon Kinesis that are the same style of like, what do I do when data arrives? And what are the kinds of places data can arrive from, and we'll process. Machine learning libraries, again, we've seen a couple, you've seen at least two examples, I suspect, right? We've used MLlib. I suspect you've used scikit-learn. Maybe you've used like PyTorch or Keras or something in the machine learning course. There is, like I mentioned earlier, there is Dask's scikit-learn implementation. Apache Mahout is a machine learning library for some computation engine, Java and Scala at least. And Amazon has a toolkit for this kind of thing as well. And again, it of course depends here what scale are we talking about. So MLlib is designed to work with Spark data frames. So, or sorry, I guess I should say Spark ML is designed to work with Spark data frame. The MLlib is the one for RDDs. Again, is it the Spark scale? Is it the NumPy and Pandas scale? Or is that sort of in between Dask representation of the data? Okay, I think that's the sort of categories that we have seen, right? So we have seen, like on each one of these things, we've seen at least one thing on each slide. It turns out there's other ones. And again, I think it's worth knowing for sort of any category we've seen, there are other options. Picking HDFS and Yarn and Spark for this course feels to me like the obvious choice, but again, these definitely aren't the only tools that you could use to do this kind of work. Other ones are out there. Then there's the things that we just haven't had a chance to talk about. The semester is only so long. You gotta pick. So I know we do have a visualization course going on this semester. I don't know if any of you are in it. I know Nishit is in it. So again, visualization tools, again, some of these are sort of big data scale. Some of them are just not just plot your data kind of scale, but one way or another, visualize the data so that people can either, understand it or maybe interact with it. Tableau being a product, there is a student license for Tableau. If you'd like to try it out, use it for a project or something like that. Also, they have a Vancouver office if you're into that kind of thing and looking for work. Maybe Tableau is a interesting one to look at. And then, of course, on the sort of smaller scale of data, there's things like Matplotlib for Python that will draw many useful visualizations. Plotly, I see. Plotly is no longer a nice open source library. Now it's an enterprise service company. But anyway, Plotly is a nice library that you can use to plot data. I'll see if I can update that to a more generic URL. ETL tools I mentioned last week. Again, for my money, I think I already have a perfectly good ETL tool, and I already know how to program and I already know how to manipulate data. But again, if it's something you're doing a lot of, or you want to sort of put into production a little bit differently or something like that, some of these more bespoke tools from the Hadoop projects or from Amazon, or I mentioned NiFi last week, or possibly Nefi. I'm not sure I know how to pronounce it. Okay, message queues probably should go before the break there, because we have seen Kafka. I have messages one way or another, and maybe this goes, we haven't really seen it because we've done a very limited amount of streaming out of Kafka. For example, you have never produced a message and put it into Kafka. So you've really only done a very limited amount of stuff there. But all of these are fundamentally about message passing. And I have a message that I want to be received. And the message is something like, here's a new piece of data that has to be processed, or here's a function, like I would like you to do computation on these arguments or something like that. And maybe then a result has to come back in the other direction. But I don't want to worry about load balancing and reliability. And if I have 10 people receiving messages, what if one of them disappears for a few minutes because the computer reboots or whatever, or what if one of them's overloaded? Let's have somebody else do that. They will worry about who is going to receive which message. I just need to know that every message will be received. I mentioned RabbitMQ earlier today, and we'll do it. Well, I guess we'll use it in a demo. But yeah, like fundamentally, the idea here is you send your messages out with some information about sort of how they will be distributed or how they have to be received. ZeroMQ, another open source library for this, or Amazon's service that does the same thing. So yeah, like publish and subscribe are often the sort of interactions that are going to happen here. I like the RabbitMQ tutorials. If nothing else, they have this very simple, like, okay, we have a publisher and a consumer, or we have a publisher and many consumers. And what we know here is each message will be received by one of the consumers. So this is something like a work queue. Okay, like I need this piece of work done by somebody. As a producer, I don't care who. And then I have as many consumers as necessary to get the work done. Or, I have this fact and each one of my data centers needs to receive this update or something like that. Or the remote procedure call style, which is somebody wants to effectively call a function. The request is, here are some function arguments. Somebody is going to be a consumer and is going to process that, do the work, generate a result, and then the result is going to come back the queue that the client is going to receive it on. So effectively, this is function arguments and return value, but with RabbitMQ in the middle, so I could have 1,000 copies of the worker. RabbitMQ will take care of making sure all the messages go in the right direction. And also, now that I see that, these are also all language independent. So I could be doing the client in Python code and I could write the server in C#. And as long as they can both speak RabbitMQ in this example, no problem. 1 million messages per second is a lot. 1 million messages per second is like more than the SMS volume in the United States. This is the scale that these things are comfortable working at. So like whatever kind of streaming data you have, I'm going to bet these message queues, again, I'm talking about RabbitMQ because I've kind of used it a bit more, but again, Kafka, I'm sure Amazon can scale that way as well. ZeroMQ is a little bit more point to point. It's not designed to scale out quite the same way. So maybe the kind of thing that you might end up doing here is something like you're doing some streaming and you want to kind of break that up into pieces. So I'm gonna have a streaming input. I'm gonna do a little bit of work in Spark, and then I'm going to publish the results into Kafka or RabbitMQ or whatever, and have some workers that take care of writing those to the database or whatever it is. Maybe I can use this to do big data, as I mentioned a little while ago, with something like Celery. If I just have a lot of consumers, that one, something like this, where I have work being generated, and okay, I put a bunch of work into the queue, and then I have 5 consumers, each one of them is doing some work. And if it's not fast enough, I add a few more consumers, and now I have 7 or 8, and sort of work through the queue and let RabbitMQ deal with it. Sometimes just moving the bottleneck is a good goal. So I have a demo here. The code is all here. I have a RabbitMQ server started up already in a Docker container here. And let's see if my demo is going to work today. Okay, so I need a couple of windows. I have this started up. I'm gonna cheat a little bit from my slide because I do have these. They're running in Docker containers. So instead of Python 3 program, I'm going to, in a Docker container, run that program just because it was easier for me to get the demo running that way. But what I'm doing here is, so this is this code. I'm using RabbitMQ, the RabbitMQ library for Python, and I'm just doing this. So I'm just publishing a bunch of messages. They're currently being queued up. So right now, I'm not actually processing these messages. My producer is just producing, and I guess I imagine these are big data tasks or whatever. Nobody's doing tasks. RabbitMQ is just dutifully queuing up these messages so they can be dealt with by somebody later. Somebody is going to be something like this Rabbit receiver.py that's going to receive those and I imagine do some work. So it's not really doing anything, it's just printing a line here. But what's happening is, again, this process over here is producing messages, this process over here is consuming them. Or what if I have somebody else doing this? So now I have two consumers. So again, the jobs are still being produced at the same rate, but now I have two different consumers that are doing the work for me. One of them seems to be getting the odd numbers. One of them seems to be getting the even numbers. I don't know if that's a rule. But now, like, if one of them stops, well, that's fine. The messages are just getting queued up. This one's now getting all of them. And if it falls behind or it stops, well, RabbitMQ is still queuing up those messages and they can still be processed by, again, whoever can process them kind of as quickly as possible. And then, again, there's nothing that says I have to produce these messages in Python. I could, oh wow, what just happened there? Sorry, it opened up. That was weird. It opened the my Ruby program up in some completely other an ebook reader. Okay. So there's nothing that says I have to produce all of these messages in Python. I can produce exactly the same RabbitMQ message in Ruby or Go or whatever other programming language I've got going on. So if I start up that, so now I've got two programs producing messages, the Python one and the Ruby one, and they're getting received by whoever. Again, whoever happens to be here ready to receive messages on this queue. It doesn't care what language they came from. It doesn't care how many are queued up. It just will process them as it can. Again, that's nice. It's nice to have that sort of assurance with a message queue in the middle, making sure everybody gets received exactly once. Kafka, I mean, the same kind of thing is going to happen here in Kafka. This you can run. This code is ready to run in the gateway. You can run all of these things in a couple different windows. A few to receive some messages, one to produce some messages. I'm going to let that go. But the code is there. It will work, I promise. A little bit higher level tool is something like, well, a more explicit task queue. So again, I mentioned celery earlier. The idea here is I'm effectively calling a function over one of these message queues. So I have something like, RabbitMQ in the middle. One side I make a function call, the other side evaluates the function and sends a return value back. That's basically what's being described by this remote procedure call pattern here, except somebody else is going to take care of the mechanics for me. Celery does it in Python. There's a few other things in this pattern. And of course, if you have any message queue, you can, send the message with function arguments, send the message with return value. But again, these are nicely high level, right? All I really want to do is call a function. I don't care maybe where the function runs. So this code, which window's which here? Okay. Okay, let's stop the, okay. Thing. This I just pretty much stole from the tutorial. But the idea here is I create this Celery app. We're gonna talk to each other over RabbitMQ, and somebody is going to start up. Well, I already have a RabbitMQ server. Again, where's my cheat sheet? There. Somebody is going to start up and be a Celery worker. So this process is ready to do the work, and my code is here. So the work is pretty simple, right? So I have a normal Python function that's been decorated to be a Celery task. That's all I really need to do from the on the programmer side of things. And then I have this thing started up that's a Celery worker. It's ready to evaluate these functions when I need them done. And in fact, let's start up another one. So, right, so I imagine I have two computers that are sharing the load. Both of them are capable of doing function evaluation for me when I need it done. And then if I actually kind of get the work started, so import the thing from that module. So this is just, I'm just going to import, there we go. Literally, I'm going to import that function from this module. I'm not really caring too much about Celery over here. It turns out I can just call it as a function, right? So there was no, this is just a normal Python function call. Or I can call it as a Celery task. So that was a message just got sent into RabbitMQ. So one of these workers, it was this one, receives the message and says, oh, you want to add those two numbers? Okay, I'll do the function call. I'll return the results. And then the result got sent back into this asynchronous result object. By the time I told that whole story, my computer was done adding two integers and I got my 9 back. But this could be, again, like any arbitrary amount of work with a bunch of database calls or whatever. And on this side, I could wait for the result or not. I could just say, please do it. And assume that it will get done and trust that it will get done because of all the mechanics that are ensuring that one of these workers is going to evaluate that function. And again, that's nice. And the more workers I have, the more sort of big data-ish I am. This is a really useful way to get work done. And it turns out you can have scheduled tasks. So you can have just like on your server, a scheduled Celery task that is do this thing at 3 in the morning, like go and pull the data from the transactional database and bring it into the data warehouse. And again, if you have a lot of work happening, let it queue up. Maybe that's okay. Like Celery is used in courses to send emails out. Like when you get the notification that, you know, assignment N marks are done, what happens is on the server, like in the web server, it sends a Celery task that is, go send 100 emails, please. And okay, that takes a while. You know, they're rate limited, so we don't overload the SFU email thing. That's okay. They can queue up. Those messages will go out. You will get the email, you know, 30 seconds after your friend. That's okay. Okay, another category here that we haven't seen. Right, we do have a like web search, like text processing and web search course that GenPay does at the undergrad level, but none of you will have taken that, I don't think. So, but these are, in some sense, these things are just databases. You know, they're store a bunch of data, but store a bunch of data specifically imagining that I'm going to do a text search on them. So I'm not just going to retrieve by primary key. I'm going to retrieve by like find me documents that have this kind of text in them. So Apache Solar and Elasticsearch are probably the two like freely available ones that are that I guess you might look for. Lucene is actually the foundation project of both of them. Both of these things are implemented on top of Lucene. My understanding is that Lucene is not there for normal people. Solar and Elasticsearch are. It apparently is a difficult thing to work with. Or once again, the cloud providers will provide if you like. Okay, so I think I have an Elasticsearch up and running in a Docker container here as well. Let's have a look. Again, let's kill off some other things. So what I'm doing here is, I have a bunch of documents. So I have effectively primary key 1, and I have field, body, and author, and primary key 2, and these two things, and primary key 3, and those two things. I'm going to connect to Elasticsearch and then index each one of those documents. So in a sort of a bucket named comments, I'm going to index each one of those. I think that's all I need there. Okay, so if I do that, and again, I have a cheat sheet on the next screen to do that in a Docker container. Okay, I've got to update my Elasticsearch code. That's fine. That doesn't bother me at all. And then when I want to search for that, or when I want to search in that, so I'm looking for the word comment. So I should be able to find it in these different cases. Search for that string in that field. And it goes off, and Elasticsearch presents its results in the format that it does. So it found those two with whatever options I had. Elasticsearch is designed to scale out. You can have many Elasticsearch servers working in a cluster. So hopefully at some large scale, things will still work. It's a pretty simple API too. Like, it's effectively just this really simple REST call. So you can just, in kind of any language, make a request. It sends back a JSON response, and you can do what you want with it. I guess I don't have sort of partial word indexing going on here. Again, it's a really handy tool to have. And again, it does scale in a really nice way. So legitimately is a big data tool. If what you have is text and you need text search, I don't think there's any question these are tools for the job. Postgres can also do full text indexing on fields. But again, if you're doing a lot of it and text search is really what you're sort of primarily doing, I think Elasticsearch and Solar are great tools to look for. Okay, one more tool that I mentioned. I've mentioned these it was 2 weeks ago, I guess. But if you want to install Hadoop, maybe again, let Amazon do it for you. So Elastic MapReduce is effectively give me some virtual machines and install like Hadoop or Spark sort of tools on them. This is probably the easiest solution. The Hadoop distributions, Cloudera and MapR, are quite, relatively simple. Like, configuring Hadoop is not as hard as it seems when you first look at it, but it's not trivial either. The distributions are, I want this installed. Please give me some good defaults. Give me a nice web front end where I can tweak the configuration and make sure things are running. That's great. Again, I think for most people, most of the time, by the hour from Amazon is the most likely way to set up Hadoop. But these other things are there. There's no shortage of things that I haven't talked about, certainly. There's a few cool, like the Spark Summit and the various like Databricks conferences that are, I assume, online conferences now, which actually makes it easier for you to attend. if or when you're in Vancouver and if or when these meetups get started back up again, there is kind of an active community in Vancouver of data sciencey kind of meetups. Some a little bit more big data like, some not. I guess these are broader searches. But again, there are Vancouver instances of many meetups like this. Have a look, and like if you are somewhere else in the world and if meetups are actually happening at the moment, it might be worth, connect with a few people before you come to Vancouver or whatever, or if you're in Vancouver, or if you have some time again when things are opened up or whatever, or do it virtually. I think that meetups are a good way to connect with people that you maybe wouldn't get a chance to otherwise. We have co-op. Co-op will help you meet people in the industry. That's great. Job fairs will as well. But of course, doing co-op is something that is like, you have to be a company of a certain size for going to a job fair or hiring co-op employees to make sense. A lot of this kind of work is small companies or like very small data teams within a larger company. Maybe the meetup is a good way to meet someone who, they work in a team of two, and they're never going to hire a co-op employee, but maybe you'll find somebody that way who's really interesting and really cool, maybe to work with, maybe just to know, and have as someone in the industry who you have as a contact. So I think I'm going to stop there. Well, I am going to stop there because it's the end of my lecture notes. Hopefully that survey of things was useful. Again, I think it's important to know that what we've talked about this semester isn't all of the big data things, certainly not all of the big data tools, certainly not all of the big data techniques, but I think you're in a position where you can at least learn what's out there and have at least some idea of what's there. And hopefully, if the time comes later, think, oh wait, I heard about it. There's a thing that does this. I don't have to solve this problem. This has already been solved. I can find a library, find a package, find a server, toolkit, whatever that will do it for me. Otherwise, I guess we're ending lectures here. Obviously, this is not a lecture-focused course. Hopefully, the lectures were useful anyway. Between now and the end of the semester, we'll see you in the lab times. Those will be continuing. And good luck on the last assignment, or if the last assignment's done. Have fun in the project. Hopefully you get cool results there, and see you in the labs. Bye, everybody.